Okay, so today I want to discuss this problem, which is a problem in calculus. And calculus problems, real analysis slash calculus problems are perhaps the most common problems in Putnam and many of these types of competitions, college level competitions. This problem is from 1992 A4. So it's not such an easy problem, although it's a pretty old one. So the fact that it's old, it means it's a little bit easier than in A4 of, say, 2019. So let's look at the problem and see what are some ideas that come to mind. So we are given a function that is infinitely differentiable, and from R to R, and we are given some relation between, we're basically given the value of the function at all of the 1 over n. So it's just only a countable set that we are given the values of the function. And the question is asking us to find the derivative of f at 0, second derivative of f at 0, third derivative of f at 0, and so on. So this is seems a bit strange because we are trying to find all of the derivatives of f at 0 with only values of f at only accountably many points on the real line. So we are given f of 1, f of 1/2, f of 1/3, and so on, f of 1/4, and so on. So it doesn't seem like enough information to find all of the derivatives of f, but of course, we know this is a competition problem, so we know that it should be something that has a solution and probably a neat solution. So we'll remain optimistic. A few things that come to my mind when I look at the problem is, okay, so we're given a function that satisfies this condition. Can I come up with any function that satisfies this condition? Maybe, and this is like a really long shot, but maybe I can actually find the function f. But that seems like very unlikely, given the fact that, or in fact, like not really true, but given the fact that you don't really know what's going on at, outside of the interval 0 to 1, and even between say 1 and 1/2, you could have many different possibilities. Again, between, you know, like the values of the values at 1, you know, the value at 1/2, and so on. And if I want to put it on a graph, I basically know a bunch of values. And since these are all isolated points, I intuitively can see that I'm able to connect these in different ways. So I'm given the value at 1, and I'm given the value at 1/2. So at 1/2, if I plug in 2 into the formula, I get f of 1/2 equals 4 over 5. So, you know, it gives us something. It goes above here. So the first one, f of 1, is 1/2, and then it's 4 over 5. Between these two, you don't exactly know how it's going to get connected. So we don't really have a chance of finding the actual function f. So that's like something that might come to mind, but not really something that we can do. Okay, so far we are thinking that, well, we can't actually find the function f, so we're out of luck there. Next thing that comes to my mind is, okay, so we can't find the function f. Can I perhaps find any solution to this? So can I, so can we find some, rather than all functions, some function satisfying f of 1 over n equals n squared over n squared plus 1. So that seems like a good place to start, at least. Like, okay, I can't really find f, but can I find at least one example or maybe two examples that satisfy this, and then go from there. Okay, so that seems a lot better now, because looking at that, I can see that I can actually write this one down as f of 1 over n equals, so this is given in terms of n. So in other words, the inside, the input and the output have some relation. So if I just plug in x equals 1 over n, that gives me n equals 1 over x. And if I substitute that into the function, I get 1 over x squared, 1 over x squared plus 1, which gives me 1 over 1 plus x squared. Okay, so this is certainly one solution. So f of x equals 1 over 1 plus x squared is a solution. Okay. By no means this is the only solution. But for some reason, they asked us to find fk of 0, which means fk of 0 should not depend on what function f I'm looking at. So that's interesting. So that tells me that the function f that I have, even though I know that's not the answer to the problem, but I should be able to find f prime of 0, f double prime of 0, and those would be my answers. Although that would not be acceptable. I can't say, well, here's a function that satisfies this condition, and here are the derivatives of that function, therefore these are the answers. So that there's a huge gap here. And given the way that Putnam problems are graded, you are not going to get much credit for a solution like that. This is not really a solution. So we essentially need to do two things. First, evaluate the derivatives of the function that we found, 1 over 1 plus x squared. And second, show that those values are exactly the same for any other function satisfying the condition of f of 1 over n equals n squared over n squared plus 1. So these are two things we need to show. So first, find fk of 0 for f of x equals 1 over 1 plus x squared. That might help because it could help us understand what are we trying to prove. And second, find fk of 0 for every f. So for every f satisfying the given condition f of 1 over n equals n squared over n squared plus 1. Okay, so both of these seem a long shot, but I mean, the second one seems to be a difficult one. It seems to be maybe like that's actually the most difficult part of the problem. But the first one seems like plausible because I'm trying to find just a function that I have and I want to find all of its derivatives. Okay, so it seems reasonable. Maybe we have to find the derivatives and then plug in values in there. So let's do that. And this is all of that. All of what I'm doing now is my scratch work. So we'll see how we can put that together into a solution. Hopefully we can come up with a solution at the end of all of this. So let's take the derivative of that. So derivative would be, you could take the derivative. I would just use the quotient rule. You could use chain rule, whatever method that you want to use. So derivative of numerator times the denominator, which is 0, minus the derivative of denominator times the numerator. So that's what we get. And that gives you that f prime of 0 equals 0. Okay, so it's interesting. I was able to find the derivative of that at 0, and it ended up being 0. So, you know, that's something that we already knew that we would be able to do. But we could start doing f double prime. And that would be a bit more challenging, but still manageable. So I'm doing the quotient rule again. Derivative of numerator, which is -2 times denominator, minus derivative of denominator, which I have to use chain rule, and then times numerator, and then over denominator squared, which is what we have. So we can simplify that, and we get -2 times 1 plus x squared plus, so it's 8x squared over 1 plus x squared cubed. So we get 6x squared minus 2 over 1 plus x squared cubed. So that's f double prime of x, which gives me f double prime of 0. Okay, I'm sorry, minus 2. Okay. So we can do the same thing again. We could take the derivative of that and then find the second, third derivative and then plug in 0. If you do that a few times, you'll see that it's actually not very difficult, not very easy to see a pattern there, if there is a pattern. So what I think about when I think about this problem, I realize that, well, I'm basically trying to find all of the derivatives of this at 0. So what does that mean? This reminds me of Taylor polynomial, or Taylor series, in fact. So finding fk of 0 is the same as finding the Taylor series for this function. So that's what I'm really looking for. I'm looking for a Taylor series for this function. Okay, but my function is 1 over 1 plus x squared. Well, we already know the Taylor series for this function. If you just think about that, this is just a geometric sum. So first term over 1 minus common ratio is an infinite sum, is a infinite geometric sum. So that's the sum, negative x squared to the power of n equals 0 to infinity. Of course, there's some restriction. This is if absolute value of x squared is less than 1. But that's really not going to matter because you're looking at a neighborhood of 0. Okay, so that's very nice because I can now say that derivative of this function, the nth derivative of 1 over 1 plus x squared at x equals 0 is equal to the coefficient of x to the power of n in the sum negative 1 to the n x to the power of 2n. So that's nice. Well, the derivative divided by n factorial, because that's the coefficient of x to the power of n in the Taylor polynomial, or Taylor series rather. So that's, you can easily find that derivative then. So you say the derivative, the nth derivative of 1 over 1 plus x squared at x equals 0 is going to be, essentially it's going to be negative 1 to the power of n times n factorial if, let's see, if n is even and I have to change that to n over 2. So, because it's x to the power of 2n. So this exponent would have to be turned into n. So this would be n over 2 and then n over 2 factorial. And if n is odd, then there is no x to the power of n in that Taylor series. So it becomes 0. So that's the derivative of that at x equals 0. Okay, so we did one of the tasks that we were trying to do. So fortunately, it ended up being not that difficult. So we found the nth derivative of f at 0. But that was only for this particular function. Unfortunately, we are left with everything else. We are essentially, if you write down this in a Putnam exam, then you're probably not going to get much credit. Maybe 1 point, probably 0 point. So we have to somehow connect this to every single function satisfying that condition. So the question now is, How am I going to be able, now that I know what the answer should be, how am I going to be able to relate those two things? How am I going to be able to relate one function, one answer that we know, because this is a problem in a competition, we know the answer. How am I going to prove that this answer is true for every single function? So that is where I think about the fact that, well, I only have one function satisfying that. So if I take the difference of these two functions, then I get something that is 0 at every single 1 over n. So this is easier to deal with that. So what I'm suggesting is to do this. Take the function f of x that satisfies the condition that they gave us, and subtract 1 over 1 plus x squared from that function. With this new function, we know that g of 1 over n is just 0 for all n greater than or equal to, basically for all positive integers n. So essentially what I did was I reduced the problem, or I kind of changed the problem from f of 1 over n being something weird, something like n squared over 1 plus n squared, to something much nicer. F of g of 1 over n is just 0. So if I can solve the problem for this, then I'm going to be done, because I know the derivatives are of 1 over 1 plus x squared. So if I can solve it for this particular function that satisfies it is 0 at all of the 1 over n, then I'm done. Okay, so that's what we're going to do now. We're going to see if I can find a way to show g must be, essentially what I'm trying to do is I want to show that the derivatives of g are all 0, because g is a difference. And I know that the question must be true again, because it's a competition problem. I know it must be true. It must be the same for every function. Therefore, we need to show, there's really no other option. We need to show that gk of 0 is 0 for all k. So that's what I'm trying to do, given the condition that g of 1 over n is 0. Okay, so let's see what we can do. First of all, before I can get to the g prime, because if you want to find g prime, you would basically, the definition would be g of x minus g of 0 over x as x approaches 0. So even before you can find g prime of 0, you need g of 0. So the first task would be to find g of 0. But, well, this function is a continuous function, and g of 1 over n is 0 for every n. So g of 0 is just the limit as n goes to infinity of g of 1 over n, because it is a continuous function. 1 over n approaches 0, therefore g of 1 over n approaches g of 0. So that is nice, because I know g of 1 over n is just 0, so the limit would be 0. So g of 0 is 0. Okay, so that's like essentially like the first thing is out of the way. So that's nice. But we are far from there yet. We need g prime of 0. Let's plug that into that. So we get g prime of 0 is g of the limit of g of x minus 0 over x as x approaches 0. Okay. Unfortunately, I don't really have any information about g other than the fact that g of 1 over n is 0. Well, that's nice, because 1 over n is a sequence that approaches 0. So if I plug in 1 over n for x, I get this. But that is exactly 0, because g of 1 over n is 0. This quantity is 0. Perfect. So we're getting closer, but still an infinite number of derivatives to go. So, it seems like maybe we didn't make a lot of progress, but We're getting closer. Okay, so let's find out what is the second derivative. Second derivative of that is the limit g prime of x minus g prime of 0 over, g prime of 0 over x as x goes to 0. Good, so let's do the same thing. So limit g prime of 1 over n, because I know that g prime of 0 is 0, over 1 over n goes to infinity. Okay, that is like really problematic because I have no idea what g prime of 1 over n is. All I know is that g of 1 is 0, g of 1 over 2 is 0, g of 1 over 3 is 0, g of 1 over 4. I have no idea what the slope is at 1 over n. It could be not 0. We have no idea what the slope is, because all we know is that these are the roots. So what is g prime of 1? For all we know, the function could be like this. What is g prime of 1 over 2? For all we know, g prime could be like that. And of course, it has to come back. So what do we know about g primes? Basically nothing. Okay, so that's a bit problematic, and you might want to give up at this point, but we did all that for essentially nothing at this point, because we don't really have an answer. We only know what the final answer would be, but we don't have a proof for that. Okay, so we have to ponder a little bit more here and see, well, what can we do? Well, if I can find a sequence, just any sequence, whose derivative g prime at that sequence is 0, that would be enough. I don't need to have a sequence g prime of 1 over n 0. I can have any sequence. So if we can find some sequence, doesn't have to be 1 over n, xn approaching 0 such that g prime of xn is 0, then we are done. There's nothing special about 1 over n. The only thing that is special about 1 over n is that it approaches 0. So if I can find a sequence, just any sequence, that derivatives at that point, that sequence are also all 0, then I'm done. So what am I going to do? Can I do that? Well, of course I can, because look at the graph that I drew. I know, because I know that the value of g of 1 and g of 1 over 2 are both 0. I know there's going to be a horizontal line here. I know there's going to be a horizontal tangent line there. And I know there's going to be a horizontal tangent line here. And if you think about that, that's what we call mean value theorem or Rolle's theorem. So those are going to be the places that you get for your new sequence. So now, putting all of that together, we can get a really nice solution here. So let's put all of this together to get a nice solution. Okay, so we'll write down the claim at the beginning first. Anytime I write down the solution, I write down the most important part of the solution, which is the claim, what I'm trying to prove at the very beginning. So I have that. Oh, and by the way, this should be, yeah, this should be n factorial, not n over 2 factorial. So it should be n factorial. Yeah, I just made a mistake here. Yeah, because this is n factorial, and you have to look at the other side and find out what's the coefficient of x to the power of n. Coefficient of x to the power of n is going to be -1 to the power of n over 2 x to the power of n. So yeah, so this is the correct answer. So we're going to start writing down the correct answer. So here's what we're going to do. So we will show fk of 0 equals -1 to the power of k over 2 k factorial if k is odd, and 0 if k is even, and 0 if k is odd. Okay, so that's what we're going to do. Okay, so I'll put that up there. So note that g of x equals 1 over x, 1 plus x squared satisfies g of 1 over n. You don't have to explain where you got the g of x from. They don't care about the fact that you got it from, what process you had in mind and ended up with that formula. It doesn't matter. So I'll just make sure that my logic is correct, make sure that everything is explained well, but you don't have to explain anything about how you got your solution. Okay, and this means f of x minus g of x equals h of x satisfies h of 1 over n equals 0 for all n that are positive integers. Okay, so now I'm going to write down my claim. The claim was, so if you go back, this is what was my main claim, that I'm going to be able to find a sequence that approaches 0 whose derivatives are 0. And then you can apply the exact same thing to that sequence and get a new sequence. Again, Rolle's theorem applied to that sequence. So this is the claim that we're going to prove. For every positive integer k, there is a sequence xn approaching 0 such that, let me also write down that xn is decreasing and if k of xn is equal to 0, or I guess hk of xn is equal to 0. Okay, so that's my claim. So I'm going to prove this claim. We will prove that by induction. Okay. So note that h of 1 over n is equal to 0. This proves the claim for essentially k equals 0. It's like basically the 0th derivative, which is the function itself. So we proved it for basis step. Now, by Rolle's theorem, there is a value yn inside xn minus 1 xn such that, or I guess xn plus 1 xn, because that was a decreasing sequence, such that h k plus 1 of yn is equal to 0. This completes the proof of the inductive step. So assuming that it is true for, so I guess I'm going to mention that assumption here to just make it a bit more clear. I think that's probably okay for a Putnam problem, but I want to make it like completely clear. So I'm going to add the assumption at the beginning that I'm assuming that hk of xn is equal to 0 for that sequence h, for that sequence xn. So suppose hk of xn is equal to 0 for a sequence xn approaching 0 with xn plus 1 less than xn. Okay, and I could also add here that it is strictly decreasing just to be even more clear. So this completes the proof of the inductive step. Yeah, so I guess since yn is less than xn greater than xn plus 1. So, and then that would be more than, so you could add that this is more than yn plus 1. And xn approaches 0. Okay, so that completes the proof of that. So since hk is continuous, hk of 0 becomes the limit as n approaches infinity of hk of xn, which is 0. Therefore, fk of 0 is equal to gk of 0, because h was f minus g. Now note that g of x is equal to 1 over 1 minus x squared, which is the sum negative x squared to the power of n equals 0 to infinity. Therefore, the coefficient of x to the power of k in g of x is k of 0 over k factorial, which is equal to either 0 if 2 doesn't divide k, or negative 1 to the power of k over 2 if 2 divides k. Because that's basically how we get how it is done, what the Taylor series shows. Therefore, gk of 0 is equal to negative 1 to the power of k over 2 k factorial, and 0 if 2 divides k, if 2 doesn't divide k. And since fk of 0 equals gk of 0, we are essentially done. Okay, yeah. So this is an interesting problem, and I wanted to show you like how you actually obtain this solution by going through this process.